So let's take a look at how you would prove this for divisibility for 11, right? So this idea is still exactly the same. So like we would start out with this number here, right? So we would start out with the number an minus 1, an minus 2, dot, 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 a2, a1, a0. So again, we do the same idea. We would write it as an times 10 to the n plus an minus 1 times 10 to the n minus 1 plus a of n minus 2 times 10 to the n minus 2 plus dot, 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 plus a2 times 10 to the 2 plus a1 times 10 to the 1 plus a0 times 10 to the 0. So this is the exact same as what we just did before, except this time it's very similar to what we did with divisibility by 9. So for 11, this is where like properties of modular arithmetic become like very, very like handy, right? So like, oops. We can remember that like in modular arithmetic, we can kind of have like negative remainders. So like we can kind of say like, so first, clearly I could say 11 is congruent to 0 mod 11, right? Like that's pretty obvious because 11 leaves a remainder of 0 when divided by 11. So if I were to subtract 1 on both sides, right? If I subtract 1 on both sides, I would get 10 is congruent to like negative 1 mod 11. So 10 is congruent to negative 1 mod 11. And this is like very similar to like the previous one, right? In the previous example, we had like 10 is congruent to 1 mod 9. But then in this case, we have 10 is congruent to negative 1 mod 11. And the reason this is helpful is because now we can replace every 10 with a negative 1 instead. So like we can replace this 10, this 10, this 10, this 10, this 10, and this 10. We can replace all of them with negative 1s instead. So if we were to take modulo 11, right, we would have like an, and instead of every 10, we can replace it with a negative 1. So negative 1 to the n plus an minus 1 times negative 1 to the n minus 1 plus a of n minus 2 times negative 1 to the n minus 2, and like so on, right? Plus dot, 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 plus a2 negative 1 to the 2 plus a1 times negative 1 to the 1 plus a0 negative 1 to the 0. So, and this is congruent to that mod 11. And this kind of like concludes the proof, right? So like we can kind of like, I guess you could do casework on whether n is even or odd, but what this just notice that like, let's say like, just to make it more clear, right? Let's say we had like n equals 5 or something, right? Or let's say n equals like 4, just to make it more clear, right? Let's say n equals 4, just to make it more concrete. So you had like a4, a3, a2, a1, a0. So you had like a 5-digit number, right? Then this formula here, if n equals 4, if you were to plug in n equals 4 into this expression here, you would get a4, negative 1 to the 4, which is just 1. Then you have plus a3, negative 1 to the 3, which is minus a3. And then a2 times negative 1 to the 2, which is plus a2. And then you can continue this pattern. Notice like it's alternating, minus, plus, minus, plus. So this kind of explains why. Notice that what this is doing is you can kind of regroup these as like a4 plus a2 plus a0 minus a1 plus a3. And then a4 plus a2 plus a0, like this green portion here, that just represents these numbers. And then like a1 plus a3, that represents like these numbers. So that kind of tells us like why we kind of like alternate between we take every other digit. Like in this case, we take the green numbers, then we take the yellow numbers, and we take the green numbers and add them, then we take the yellow numbers and add them, and then we take the difference. So this is the n equals 4 example, but this can easily be generalized to like higher values of n. And yeah, so that's how you would prove divisibility for 11. It's very similar to divisibility for 9.